Okay, here's a topic that's usually pretty popular. It's called randomized tree metrics. So to frame it, let me remind us what we've been doing. So so we've been doing some of these like metric embeddings and stuff related to metrics, starting with this dimensionality reduction last week, right? Trying to go from a higher dimensional Euclidean space to a smaller one. And then last time we did something that's sort of a more combinatorial version, where we tried to go from any metric and embed it into basically a bunch of line embeddings, which turned out to be exactly what you want for things like flow problems, like sparsest cut. Okay, so this connection, yeah, cuts and L1 metric embeddings have this nice thing. So today we'll do another kind of embedding into trees instead of into lines. So, okay, just to remind us, I guess you guys already know this. This is a metric, right? Okay, it's going to be symmetric and positive and all these good things. Um, and yeah, there's of course like geometric metrics like Euclidean metrics, but often we like things like shortest path metrics, cut metrics, which are metrics induced by cuts, so on and so forth. So, okay, I put together some problems about metrics just to highlight how important the ensuing technique will be. So, for example, something like buy a bulk network design. Let me read this because I haven't read it in a while. Okay, this is a problem that actually came up a lot when they are trying to lay out, Bell Labs is trying to figure out where to put cables. So you start with an undirected graph, and you have edge lengths for all the edges, and then you have demands. Okay, and and then you have this sub-additive cost function on every edge. Okay. So what you want to do is for every ST pair, choose a path. That's like where you're going to lay the network. You're going to lay the wires. It's like buying a path. And the idea is that if 10 different people are using this wire, okay, I have to buy more wire, but the cost maybe is going down on a per unit of wire basis. Okay, so yeah, yeah, yeah. I'm explaining. Yeah. Okay. So imagine the graph is like where you could put the wires, okay, or where the path can go. So you're going to choose one path from between every pair of nodes, maybe up to this demand, and or maybe you can just think of BST of being one just for simplicity first. So you need to have a path between every pair. So imagine a path will correspond to actually laying out some amount of wire really from S to T, a unit of wire. Okay. Now for a particular edge, there may be many ST pairs using it. So if I buy like 10, enough for 10 connections or something, right? So this part is saying that so sub-additive is like really saying like, okay, the cost of buying 10 should be more than 10 times the cost of buying one. There should be less than. At most, less than? What did I say? Okay, at most, less than the cost of buying 10 cables of unit one. So it's like saying you can go to Costco and you can buy a lot of uh, cost on a lot of wires over a single edge for a discounted price. Otherwise, it's just coming from like an Oracle. I mean, you don't assume any more structure other than it's sub-additive. So it's some kind of like economic looking thing. So, so for that reason, when you choose your ST pairs, you might want to choose, common edges to try to get a discount. Okay. And so that's the idea. So here, once you've picked a path for every ST pair, then the total capacity that's being used on the edge is I'm summing over all ST pairs that are using the edge, the demand, which could be one. So that's the total number of ST pairs using the edge. Okay. And then you're going to pay your discount price for this capacity times the length. of the edge. So this cost is like a per unit length cost. Okay, so this is very close, or this is a reasonable model for your AT&T trying to build out the internet. Yeah. Yeah, so it's just a model, but so F sub E is really giving you the cost per unit length, the cost of 10 units of wire for how long the wire is from point A to point B. I guess the problem would still be interesting even if these were all ones, but in the more general setting, it could be bigger. No, the sub E means that we can have a different function for every F, for every E. Couldn't L be absorbed into the function FE? Yeah, I think so. Did I just get a notification? Okay, I don't know. Yeah, maybe, maybe. Um, yeah, that's possibly true. Yeah, I mean, it's just a real valued function. Is there a submodular version? Well, I guess so. I guess so. Um, yeah, maybe one can do a submodular function and that will take as input all the pairs using the edge and output some value. And whether that has been studied, I'm not sure, but it sounds natural. It would be more general than this. Okay. That's one example of a problem. Now, let me give another example. This one you've probably seen before. So k-median clustering. There's also k-means and stuff. But you're given some points in a metric space, and you want to find k-centers, say like 4 of them, to minimize. You assign each point to the center you choose. So I don't know, maybe you choose this one and this one and this one, and maybe you're only allowed 4 or something. I don't know if this is a very good choice. But for every point, you're going to look at the nearest one, and that's the price you pay in distance. So it's the sum of distance to the nearest point. Okay. And so that's the k-median problem. Okay. K-means is distance squared. So this is another variety of a kind of problem that's really, the metric has all the information you need. And finally, here's another one that sort of is based on a metric. Okay, so this comes from like image segmentation. So here's the idea. You want to think of every single image, I mean every single pixel as a vertex. Okay, and uh, right. Okay, and you can think of well, I guess probably what they'll do is they'll have edges between all sorts of different pairs of pixels. Okay, and and you might assign a metric that's sort of scoring uh, how similar 2 pixels are. Okay, maybe based on some features or something nearby. And so the idea is that your goal is to assign labels to every vertex. Okay, and the objective is, okay, you have some cost function. That should probably be v times L. Okay, so you have a cost function, uh, maybe based on some prior or something, or you can maybe say, I know this is this, and I know that pixel is that, and you can make it like infinite for the pre-labeled pixels. Okay. So f of v is assigning to each vertex one of these labels. You pay a cost for the assignment, and then you summing up all these edges, the weight of the edge times the distance of the labels. Yeah. Okay. Yeah. Well, I guess I would imagine there's at least edges between every pair of neighboring pixels. That seems like a natural one. But the model is general. I mean, in this example, they probably do neighboring ones, or maybe local neighborhoods or something. I don't know. In the general version, you just have edges. And okay, sorry. So the metric is over. I think everything in the top is wrong. So one sec. Uh, okay. So we have this. We have that. Okay. So E could be like every pair. E could be every adjacent pair. I don't know, of pixels. And this is W U of V is some importance of these two times. Okay, you're paying some distance of the labels. You know, you have some prior on how similar the labels are and not. Okay, so you want to label this, and you want maybe pixels that uh, have the same color to have a higher weight or something because you think they're more likely to have the same label and things like this. So this is one way that image segmentation was modeled. Yeah. No, it's for image segmentation. See, we can highlight the person crossing the street. You start with a picture that's not highlighted. You you choose F, and then the labels and the metric over the labels is some prior. You say, oh, cats are like dogs or something, but not like stop signs. Yeah, yeah, yeah. Two nodes, U, V, E. So the weight of the edge from U to V. Vertices, yeah. And probably in this they're like neighboring pixels or something. And the weight of the edge might be like, oh, if they're the same color, let's give that higher weight. They're more likely to be in the same class. If they're very different colors, we'll give it lower weight. Or maybe you do a neural network or something, and if the features are similar, they'll have higher weight. The features are some different, lower weight. Okay. All right. That's another example of a problem. And yeah, so there's all these kind of problems that are have to do with some kind of metric, some kind of length, some kind of shortest paths uh, that are considered in approximation algorithms. They're just motivation. Okay, now those were all like metrics over some implicit graph. Now consider a tree, right? Consider the shortest path metric on a tree. What's so great about it? Yeah, it's really easy, right? So normally all pair shortest paths is really a pain, right? You need like mn time or something in a normal graph to do all pair shortest paths, right? But in a tree, like you can even pre-process it and set up your link cut trees and stuff on top and be able to query for any two vertices a distance in log n time. Okay, the pre-processing will take linear time. Okay? So trees, I mean, because there's no choice, right? There's a unique path between any two vertices. So trees are very, very nice graphs to work with. All of those previous problems are much easier for trees. Okay. So for example, consider that like buy up bulk network design thing, which seems like a very complicated problem. But here there's no choice in a tree. There's only one way to connect the two vertices. So there's a determined solution. So at a high level, if you could take an input graph and convert it into a tree without losing much, and then the ensuing problem is very easy on a tree, you might have a good algorithm. So this list is a whole list of problems that are actually addressed by what we're studying today. Okay, so what's the high level idea? So you're given an undirected graph with some positive edge weights, and you want to compute tree T that includes the vertex set as a node. It could have extra nodes, so that the shortest paths in T are very close to the shortest paths in G. Okay? And if you can do that without too much loss, and then you can solve things very easily on a tree. You know, each problem might have a slightly different detailed approach, but the point is that trees are clearly much nicer than graphs. Okay, so this turns out to be a very, very powerful paradigm. Even the best flow algorithms are doing this kind of thing. Okay, so linear time flow. Okay, so how are we going to measure it? So let's assume that the distance in a tree are only greater than or equal to the distance in the graph. Like if it's not, then just increase it so it's normalized. Then I'll say the stretch for an edge is this ratio, the distance between the two vertices in the tree versus the distance in the graph. Okay, this will be greater than or equal to 1 after scaling. And I want this to be as small as possible, like polylog would be great. And okay, yeah. Well, I've normalized it. So if it's not normalized, I could just set all the distances to be 0 or something, and stretch would be 0. So let's suppose it's normalized so the distances in the tree are always greater than or equal to the distances in the graph. Then once it's normalized, what's the stretch? Yeah, that's just making it fair. Yeah. Oh, no. Okay, so that's the dream to get polylog stretch, but it's not too hard to think of a case where you can't. So, okay, suppose I restricted it to spanning trees. Okay, so you can only pick a spanning tree. What's a graph? So you can compute a spanning tree and then use the shortest path in the spanning tree as a proxy for your shortest path in the graph. What is an example of a tough case for this? A complete graph? Okay, so if you had a complete graph, uh, let me draw a small complete graph. Okay, so unweighted complete graph, everyone has distance 1. What would be a good spanning tree for this? Yeah, so this thing actually is not bad because everybody has distance 2. So actually a click, you can find a good spanning tree to preserve all the distances. 1, 2. Well, some have distance 1, distance at most 2. Yeah. All right, so that's stretch 2. That's not bad. So that's actually not the bad case. A line? A line is a tree, so that would be great actually. So any tree would also be great. So actually it's kind of funny, right? A click is good and a tree is good. That would seem to be two ends of a spectrum. So there's something in between, I guess. Oh, a cycle. Yeah. So if you delete this edge, then these two vertices are going to be really far apart, right, for any two edges you delete. So at some level, it's impossible to get a spanning tree that makes everyone happy. Okay. Yeah. Yeah, so there's two different kinds of problems. In one version, you're allowed to add edges and even add vertices. The other one, you want to get a spanning tree. Now, okay, suppose you are allowed to add vertices and stuff. So you can build a tree on top, if that makes sense. An auxiliary tree of some kind. Any ideas? Ah, okay, you can try adding something in the middle and then add these spokes. Okay, so this will get all those adjacent pairs correct, right? Up to a factor of 2. That would be good. But there is actually something of a flaw here. Yeah, so these things are actually supposed to be far apart, and now they're only hop distance 2. So once you scale it up by n, you're still losing. Okay. So, okay, so there's two results, one of which we won't cover because it's not a randomized algorithm, but it's still worth mentioning because it's very influential. So, AKPW, a lone carp like the MP Hard Richard Carp, Peleg and West. So they showed that you can find a spanning tree where some edges are going to be screwed up. There's nothing you can do about a cycle. Um, but if you look at this, one edge has stretch n, or n minus 1. These two edges, or these two pairs have stretch n minus 2, n minus 3, and stuff like this. But actually, on average, you're not doing so bad because many edges are kind of smaller if you add it all up. So you can, in a more general case as well, get a single spanning tree where if I sum up over all the, oh, actually, you should just sum up over all the edges, sorry. If you sum up over all the edges, not all the pairs, and you average it out, you're going to get average stretch to be some smaller than any polynomial. Yeah. Yeah, summing up over the edges in the initial graph, not summing up over all pairs. And averaging. This is supposed to be an n to a little o of 1. So it's like n to the 1 over log n or something kind of weird. Or maybe log n over log n. Yeah. Yeah. So uh, so that's one thing. And they were actually motivated by online algorithms, like online algorithms where you're kind of moving around on a graph at each step. But if you're in a tree, then each step is determined, right? There's nothing you can do. There's no choices to make. So that was part of their motivation. Actually, it motivated this as well. And then today, we're going to do something like this, where we're going to take an input graph and build a red auxiliary graph on top with some edge weights, okay? And then we'll use the path through this auxiliary graph to approximate. And it's going to have two features. One is that it's going to be what's called a dominating metric. That should be d sub g, but it's cut off a bit. Okay. So, okay. So the distance will all be greater than or equal to. And otherwise, the stretch is going to be good on this sense of the word average. So it's going to be a randomized tree metric. We'll do some randomized construction. And we're going to guarantee that for every edge, the expected stretch is small. Okay. Yeah, it's going to be like log n or something. Okay. So that's what we're going to show. It's going to have an additional feature which is actually useful for some of the problems I listed before, where not only is it going to be a tree metric, but it's going to be like, have like kind of the edge lengths growing in constant power. It's going to be a geometrically increasing sequence. So down here will be the vertices from the original graph. Everything above is an auxiliary vertex. And the edge lengths here are multiplying by factors of 4. Okay. So this is called a hierarchical tree metric. And one thing great is that if I want to know the distance from this node to that node, all I really need to know is where they meet up to a constant factor, right? Because it's going to be the biggest edge that dominates their length. Up to a factor of 2 or 3 or something. So, so that's even nicer. Okay, so we'll come out with a very structured tree metric. Okay. So the thing we're going to be discussing is really coming from these two papers. The main idea really started with Bartal, who was motivated by actually online algorithms, in general, the idea, yeah, again, is that if you're in a tree, then there's only one decision you can make. So all your online decisions are forced. And Bartol was able to get a log n log n approximation factor, which is really really great. And then of course, then everyone asks, okay, is a log n necessary? And in the interleaving time, people also keep finding more uses for these randomized tree metrics, like that long list of problems. There's just, someone be like, oh, you can use it for this, you can use it for that, and it's just like an infinite number of papers. And then this group figured out how to take the log n log n down to log n, and then they immediately got optimal bounds for like all those problems simultaneously. It was often known that log n is the best you can do unless p is equal to np. So I think this paper might set the record for like most approximation bounds set in a single swoop. Yeah, they had a follow-up paper just like listing applications or some kind of survey. Um, yeah, but it's still often called Bartel trees because that's where the main idea uh, starts. And I'll explain the subtle difference between the two. Okay, so right, so this is the bound we're going to get. We're going to get an expected stretch of log n for all edges. All right, so uh, yeah, okay, so what is the algorithm? So the algorithm is very interesting. So let's say that this whole space has diameter like delta. Okay. And what we're going to do is we're going to randomly permute the points and scoop out balls of diameter delta over 4. Okay. So maybe the first point is like this one. Okay. And then you scoop out, come on. Ooh. Huh? Diameter is the furthest distance between any 2 points. And this will be like, some constant factor smaller, like delta over 4. Okay. And then imagine like scooping out all of these points. Okay. And then whatever's the next randomly sorted chosen point, you scoop all of these out. Like this. Okay. And you keep doing this. So this will scoop out more. But these points have already been scooped out. Okay, so it'll start looking kind of like this when you overlap. I guess we have a little overlap here. You might wonder, who would waste such time drawing this picture? Okay, and then I don't know, uniformly sampled. Yeah, oh, that's not right. Uh, yeah, you scoop out another one. Come on. Did I kill it? Okay. You scoop out this point or something, and so on and so forth. Come in like this. And then you'll scoop out everything at the top level. And then you're going to do the same thing at the next level, but with delta over 16 or something. You're decreased by another constant factor. So if you look inside one of these balls, now this ball has diameter delta over 4. So to do diameter over 4, you're going to get delta over 16. Yeah. Oh, yeah, you'll get diameter delta over 2. Yeah, okay. And then you divide by 4 again. Um, yeah, so maybe it doesn't matter. Okay. So you'll scoop out this smaller ball and this smaller ball. Huh? This kind of thing. So you keep doing this. Okay, I've already drawn a picture. Uh, and so you're gonna, do this all the way down, right? So you're gonna keep scooping, scooping, scooping at different scales. Yeah. Yeah, so you could redo the permutation, or you could stick with the same permutation all the way through. And it turns out we're going to analyze sticking with the same permutation all the way through. And I think if I'm correct, that was the difference between log n and log n log log n. So log n log log n actually did a different permutation, resampled a new permutation, and somehow using the same permutation made the difference. I don't know if that makes sense, but we'll see where it's useful in the, yeah. Yeah, let's say that the distances are polynomially bounded or between 1 and poly n. So your first diameter will be poly n, and once you get down to 1, you're done. So you need log n rounds or something. Yeah. Yeah, but yeah, it'll stop when all the points are by themselves. And if the diameters aren't polynomially bounded, you just kind of skip the balls that are uninteresting because, yeah, it's okay. All right, so you'll get something like this. So each of these nodes represent like the part of the graph that remains. Okay, so at the top we have the entire graph, and then we kind of scooped out these four top level things, right? And then this gets scooped out even further, and so on and so forth. Now, if you look at like two vertices that were split at the top level, we know their distance is at most delta, and it's like at least delta over 4 or something. Actually, no, they could have been very close, of course. But it's at most delta. Okay? So I'll just say, okay, if they get split, I'll assign edge length like delta over 4 here. That's a constant factor approximation of an overestimate of their distance. Maybe that should have been delta instead of delta over 4, but yeah. Okay. How do you implement it fast? I'm not too worried about fast here, but you could just pick a point, and if you're in a graph, compute Dijkstra's. You could do all pair shortest path initially, and then there's actually more clever ways to kind of get it all down to one Dijkstra for each one. But yeah, uh, but in the worst case, you can just do, yeah, you just need to compute the distances, and it's not bad. One thing kind of interesting is that if you're running Dijkstra, so the distance is sort of like, even though you scoop out the points and you're running Dijkstra later, you want to leave those points in for running Dijkstra because they participate in the shortest path metric. Yeah. Okay, so that's the high level algorithm. Here it is more precisely. So, oh, yeah, I didn't do it perfectly. I'll explain what I left out. So you order the vertices once, uniformly random at the beginning. Okay, and we'll fix it. It'll still kind of work if you read it the whole time, but we're going to fix it. And then you're going to choose this value alpha between 1 and 2 uniformly at random. Okay? And then you can see the radius, is starting from, 4 to the some I that's big enough to cover the whole graph, and it's going down by a factor of 4 each time. Except I'm also kind of like randomly stretching it out by alpha. So it's a slightly randomized radius. So it's between delta over 4 and delta over 2 or something. Okay, so there's a little extra randomness. It's roughly 4 to the I up to a power of 2, factor of 2. And then you scoop and scoop all the way down. Okay. And then the edge length that you assign will be kind of the edge length of the circle, the radius that was used to define it. And at least up to a factor of 2 or 4 or something, that'll give an upper bound on the distance of everything that's being split. Okay. Um, okay, so that's the algorithm. Now, what we need to do is that for any particular vertex, the distance in the tree, so I'm writing d sub t to be the distance that's assigned by this scooping process, is at most log n times the true distance in expectation. That's the claim. Okay, so what? This doesn't seem very interesting. Oh, that's because something in it. Okay, so we need to show this. Okay, and so let's break it down and kind of introduce some notation. So just to make sure we're on the same page, suppose k is the height of the tree. I guess I'm assuming the minimum distance is like 1. So let's say k is the height of the tree where two vertices are split. Okay. Then the tree is going to say, oh, these are roughly 4 to the k apart, because that would be the two biggest edges separating them. There might be smaller edges, but that's going to geometrically collapse. Um, and yeah, so it's going to be roughly 4 to the k. And so when they do get split, that means there's some other point W where we had sort of done some cluster centered at W and it split them up. Okay. And there's always kind of there's one cluster somewhere in the process that was the first time that U and V got split. That really determined the distance from U to V in the tree. So in that case, when W is that center vertex, we'll say that W contributes 4 to the K to the distance, because that was the vertex where the scoop really split them up. Okay. And now at the end of it all, up to a constant, the distance in the tree can be summed up as, I'm summing over all the vertices W, how much did W contribute to the distance? It's only going to be one of these, but this is kind of setting up like a linearity of expectation for us. Yeah. Yeah, so in this process, U and V will get split up once and then they're split up forever. And then when it got split up, it was scooped out by something centered at some W, which could have been V or U, but some W. Yeah, so in that sense, we're going to kind of charge, when that happens, we want to sort of charge the distance to W. Yeah, we're just trying to break down the analysis of a complicated algorithm. Question? Okay. Okay, so here is the claim. The claim is that if W is like the 10th closest vertex to U or V, so by 10th closest, I mean like U and V are the first and second closest, and the third closest is like the closest to U or V kind of thing. And the fourth is by distance, the minimum between the distance from W to U and W to V. That's what I mean by closest. Okay. So it says that if W is the 10th closest vertex to U or V, then the expected contribution from W should be something like the distance divided by 10. Okay, so it's saying that this kind of rank from U and V affects the thing. Yeah. Yeah, so that's going to come up good point. So at some level, we know that the radius is the same for all the vertices and all the clusters. So, and maybe you can already guess where the analysis is going, but we do know that for any vertex W that's closer to U and V, has like lower rank, then sort of U and V are going to be in that vertices circle first. Or it's going to, every time it's in W's circle, it's going to be in that closer vertex's circle. But that doesn't necessarily mean that the closer vertices will be the one that determine U and V, because no, sorry, huh? They can end up in the same circle. That's not quite what I had in mind. Well, what determines who scoops out who? They have to be close enough, but also who goes first. So there is some random ordering going on. So that will have to play a role. Now, okay, first to appreciate the claim, suppose it's true. Suppose the claim is true. If the claim was true, could we get our final bound? Okay, so then we can just sum up over all the vertices, right? So I guess it's this thing here. So if we kind of number the vertices W1, W2, Wn by distance from U or V, then we're going to be summing up over I uh, the expected contribution from Wi. Okay. And then you're going to be summing up over all L. I guess I could have just done I. 4 times the DUV over L. And then there you'll get your harmonic sequence. Okay. So that's the idea. Okay, so, alright, so that means I just have to focus on the Lth closest vertex and try to prove this one bound, and then the log n will follow from this harmonics series and linear expectation. Harmonics, I don't know. Okay, so this is I think the setup as usual is the most important part. Now I'm going to assume that W is closer to U than V. It's one or the other, doesn't matter which. So I'm going to fix it for our analysis. And now there's two necessary events, right? So what are the two events, or what are some things that have to happen for W to determine U and V? You know, for W to be the one that really determines the distance between them. Yeah. It needs to be ordered before all the vertices of higher rank. So that should be one of these. Let's see which one. Nope. Oh, bummer. Okay, what's the other event? I don't know how fast you read it. The radius has to be just right for W to kind of split up the two of them. So those are the two events that are necessary. Okay. And the key point is that these two events are actually independent, right? Because whether or not the radius comes in between them is just a function of alpha. And then whether it comes first is just the ordering. This is really great, right? Because it's a complicated thing, so to be able to find points to separate it out is rare. So, good. That means I can look at E2 by itself, and what is that? Yeah, okay. That's 1 over L. Okay, so we just have to worry about event 1 happening. Okay. So first of all, there's only one possible choice of K that could possibly work. Okay, assuming, yeah. Because I need to get this divided by L overall. So I just want to analyze W's contribution and and in this somewhat convoluted algorithm, and I think I'm missing your point. So if some other closer vertex was ordered before W, then it will always be scooping U or V or both before W has a chance to scoop out U or V or both. Okay, so if the eighth closest vertex, and W was the 10th, was ordered before in a random order, in that random permutation at the beginning, then W would always lose to this vertex. Yes. Yeah, this is the part where only one vertex gets to split them up. So these are two necessary events, not sufficient. Okay. Um, okay, good. So we have two cases, right? One is when the distance from W to U is actually smaller than the distance from U to V. And the other is when the distance from U to V is smaller than the distance from W to U. Okay. So, so this is sort of like, okay, let's just look at this first case, right? This is when they're kind of close. So we have some U and we have some V. And I said W is going to be closer to U, and the distance is not so bad, right? Maybe it's better if I drew it like this. So here I want to argue, uh, okay, so this is when W is actually pretty close to U. In the extreme case, maybe W is very close to U, right? So I'm going to argue this is actually a good situation for us, but why? So I'm really worried about a really big circle at W breaking up U and V, right? But if W is like, say, if W is already very close to U, if there's a circle separating U and V, okay, the radius of that circle is going to be comparable to the distance from U to V anyway. So it's not that big a deal. If it's a big circle, it'll have to swallow up both of them. Okay, so it turns out this is an okay case, right? So when W is close to one of them, one or the other, relative to the distance from U to V, then actually there's no real harm. So that's okay. So we don't have to worry about this. I'm rushing a little bit. Okay. The more interesting case is uh, is when W is like further away. Okay, did I mean WV or WU? I meant WU. Let me fix that. Of course, I won't fix it next time I teach it. Okay, so in the interesting case, you have something that's more like this. You have U, you have V, and so this is the part that's sort of dangerous, right? W is here. Okay. Now there could be a really big circle that captures U but not V, and then that will assign a really big overestimate on the distance. So that's what I'm worried about. So the first thing to point out is that because this thing is growing in factors of 4, the choice of K is unique. Okay? And part of it, what's kind of going on is what's the best way to do this? Um, okay, I'll only do a picture proof. But at some level, if this was exactly 4 to the K for some value from choice of K, okay, 4 to the K plus 1 would have to be way too big if you work through the consequences of this. It's just going to be triangle inequality. Okay, there's really only one choice of K that's going to have any overlap. Yeah. Well, it could be this could be the whole range of uh, 2 times 4 to the K or something. Okay, and this would be 1 times 4 to the K. So any value of alpha in between is okay. Yeah, so if I drew a line here, if I drew a line here, this would all split up U and V. Okay. Alpha is uniquely continuous between 0 and 1. Yeah, okay. Okay, so this is just working through this slowly. Okay, so I'm just trying to hit the punchline in the -1 minutes we have, because we're pretty close to the end and it seems like a shame to start over. Okay, so now let's look at the probability of event one happening, right? So, okay, so we have W, right? And we have U and we have some V, and this is maybe like the 4 to the K mark, okay? And okay, so in the really dangerous case, like 4 to the K is already huge compared to the distance from U to V, okay? That's where we're going to overestimate a lot. So you're picking some random distance between 4 to the K and 2 times 4 to the K, okay? Because alpha is chosen between 1 and 2 uniformly at random. So in the worst case, the odds of choosing something that splits them in the middle, okay, is going to be DUV over 4 to the K, okay, because that's, if you're inside here, then you split them up, but you're choosing it out of this interval, okay? And this is not a very exaggerated picture, a more exaggerated, like this part is huge compared to UV, okay? The point is the choice of K is unique, and then there's only one. Now, if event one occurs, then if event one does occur, then how much does it contribute at this particular choice of K? So a unique choice of K that could split it, a unique scale, and you contribute 4 to the K. So, right. So, so you'll contribute 4 to the K plus 1 if you do cut it, which requires at least these two events to occur, which were event independent. Okay? And we start plugging this in, and you get 4 times the distance over L. So you'll get the probability, which is proportional to that radius where it's being cut, to cancel out with the radius you're assigning. Some constant factor left over, that's okay. Right? So I rushed it a little bit so we didn't have as much time to absorb. So, think about it over the weekend or something. But ultimately, this is a pretty incredible algorithm, which again, that's what we showed. It resolves a number of problems. I think I'll probably give you at least one application for homework to see why this is useful. And okay, that's it for today. Thanks.